solution. So oh, I don't know what happened there. Give me a second here. My presentation mouse down. There we go. So the bottom line, the key point I want to make is not only is a secondary virtual main a great technical solution in terms of reducing system complexity, you completely eliminate that 2000 amp main breaker and main breaker section. Okay? But you get a safer system. You can see dramatically lower arc flash incident energy in the secondary switchgear, and you can deliver the system for just about the same amount of money, or even slightly less money with a secondary virtual main. The cost of the CTs and the protective relay, okay, are much, much less, a fraction of the cost of the 2000 amp secondary main breaker. Any questions? People have, you've seen this slide before, have said, you know, that I've heard authorities having jurisdiction actually challenge me that secondary virtual mains are not approved by the National Electric Code. And my answer to that is baloney. That is not true. Okay, a secondary virtual main, okay, it is not defined one way or the other by the NEC any more than the NEC defines that you have to use a circuit breaker or a fuse. Let's be clear, the National Electric Code requires overcurrent protection and defines the functionality of the overcurrent protection. It does not specify when physical mains must be utilized or secondary virtual mains. You can use either. Okay? Now, again, in order to use a secondary virtual main, you have to have control of the transformer. You have to own the transformer in order to install a primary device. And similarly, as I noted, the NEC doesn't tell you whether you have to use a breaker or a fuse. That what the NEC does do is it defines where and under what conditions overcurrent protection must be applied. So one of the questions I get as well is, does it make any difference, the distance, okay, the fact that we have CTs here, which must communicate to a protective relay, and that protective relay to the primary breaker, rather than have a physical secondary main? Does distance make a difference? And the answer to that is, thanks to the physics of electricity, no. Okay, since electricity travels in theory just shy of the speed of light, effectively at the speed of light, and the speed of electricity in copper conductor is approximately just shy of 300 million meters per second. No, it doesn't make any difference whatsoever. I want to make sure everyone's hearing me. Michael, are you hearing me? Randy, I just want to do a check. I haven't heard any feedback or questions.
Yeah, you're very clear, Bucky.
Okay, thank you. Appreciate it. I think perhaps, and I've often been asked, why don't we see more secondary virtual mains in electrical system designs for unit substations? Particularly in industrial environments in the United States. And I think part of the problem is just the name. Secondary, the very name virtual almost implies that it isn't real. And I want to be clear, it's just as real in terms of providing secondary overcurrent protection as a physical secondary main. Again, electrically speaking, okay, there's no difference in terms of overcurrent protection efficacy. In fact, it could be argued that modern microprocessor protective relays, such as pictured here, I'm only picturing 50 and 51 here, but as you can see, we can offer 87T and frequency protection and reverse power and under and over voltage. I mean, there's a variety of overcurrent protection functions that can be added in a secondary virtual main, which are typically not available in a physical secondary main. And as I noted previously, if you just look at the big red arrow here, for purposes of visualization, if you remember one thing coming out of this presentation, it would be that where those CTs are located physically on the secondary bus of the transformer, okay, that is where the overcurrent protection starts. So in terms of a power system study model, okay, that is where you model the overcurrent protection taking place, exactly as you would if there was a secondary physical main. The only difference in this case, of course, in your power system study model, is you have to model the opening time of the primary breaker and the latency time, the assertion time of the relay itself. So those two. A medium voltage device, such as shown in the primary breaker here. So in terms of NFPA 70, National Electric Code requirements, there are separate overcurrent protection requirements in Article 240. And for transformer feeder protection, well, Article 450 covers the transformers. So we've got standard overcurrent for transformer feeders in 240 and then transformer protection in 450. Neither of these sections, I want to be clear, makes any distinction whatsoever between protection with a physical main versus a secondary virtual main. And either a physical or secondary virtual main can't protect feeders or transformers as defined by Articles 240 or 450. I've, on some occasions, had to make this case to authorities having jurisdiction, and so far I'm batting 1,000. I've never lost the argument. Sometimes it takes a little bit of explanation, but I've always won the argument. So in terms of National Electric Code device recognition, again, there's no difference between that physical circuit breaker you see in the lower left-hand corner there and taking a protective relay, adding protective class, relay class, current transformers, and tripping a primary or asserting a primary overcurrent protection device. A physical overcurrent protection device, without doubt, is the most common type of electrical overcurrent protection in the United States. And while it's traditional and while it's functional, I would argue that it has several significant disadvantages in terms of safety, reliability, and maintainability. And of course, the biggest safety drawback here is the line side of that secondary main breaker. Without a secondary virtual main, if you just have a physical main, that device is, as long as your transformer is greater than 125 kVA, which is not very big, you're going to be PPE category dangerous. There will be more at 480 volts. There will be more than 40 calories per centimeter squared at the 18-inch working distance. And I've shown here a typical low voltage breaker on the left and typical medium voltage breaker, vacuum breaker on the right. Prior to quantification of arc flash hazards and the publication of IEEE 1584, the original one, and of course we had a new version of 1584 recently published, and of course NFPA 70E. It was, if you look at this switchboard here, it was acceptable to lock out the main on a low voltage UL 891 switchboard and work on the feeder section. So you can see the picture there. If you go on the lower right of the picture, you can see the main breaker sitting there, and we could see a 1600 amp feeder to the section to the left of it, and then all the way on the very left, this is, by the way, a square D QED2 I-line, pretty classical switchboard, and you can see the feeder breakers. So in the old days, we didn't know anything about arc flash. We would lock out that main breaker and we would go to work in that feeder breaker section. And provided we had verified absence of voltage face to face and face to ground and tested the tester before and after the test, we would assume we're safe. And we are safe at that point from shock hazard. But what we didn't know back in those days, okay, is that we were not safe from arc flash hazard. And I lost a personal friend of mine to an arc flash event a month before 9/11 in 2001. And when I went to the funeral and met his widow, the 3 young kids who would be growing up without a father, it had a dramatic impact, not only on the future course of my career in terms of my priority on safety and reliability, but on my own personal work habits. And I will freely admit to anyone who knew me back in those days that I was a poster child for being an accident victim. I did not follow electrical safe work practices prior to 2001. absolutely a poster child for someone who would become the next accident victim at that point in time. And I credit that event and the publication of 1584 and NFPA 70E for why I'm able to be in good health standing before you today. When we look at secondary virtual main issues and the disadvantage of physical mains, we could see that the arc flash incident energy on the line side of that breaker, okay, is almost always greater than 40 calories per centimeter squared. And I want to be clear, that means this entire switchboard is PPE category dangerous. One of the things that drives me crazy when I see power system studies, that there's people that do power system studies that know how to use the modeling software. They know how to use SKM or Easy Power or ETAP, and they know how to plug data into boxes. But what they don't take into account is the physical construction of the equipment itself. So what I'll see, and this is quite common, I see this, I'll see that two different arc flash labels on this same low voltage switchboard. On the line side of the switchboard of that main breaker, I'll see a dangerous arc flash category, and then they'll take the overcurrent protection of the main circuit breaker, okay, and calculate a lower arc flash incident energy on the remainder of the switchboard. And that is absolutely a flawed methodology, because if the arc flash takes place on the line side of the breaker, it will absolutely propagate through the switchboard. Just as in shock hazard events, electricity follows all paths, but favors low impedance paths. And in an arc flash event, the rapidly expanding pressure and plasma wave, okay, favors low air pressure paths. And the low air pressure path is first inside that switchboard itself and through openings and vents and seams. So if you're working on the left-hand side of that I-line section, you're replacing a breaker, and at that point, a tool from the previous maintenance outage falls between two faces of the primary bus, it could very well create an arc flash event and kill you, despite the main breaker being locked out. So there should only be one, I want to be clear, there should only be one arc flash label on the switchboard, and it better be labeled PPE category dangerous, saying no personal protective equipment is safe. Any questions at all? So when we look at, just to wrap up on physical mains, whenever you have a close coupled physical overcurrent protection, it's no longer acceptable, okay, to just lock out that device and include and assume that the close coupled equipment to which you're connected to, okay, is an electrically safe working condition. The same concern applies to all close coupled physical mains, and I don't care whether you're in a low voltage or medium voltage system. The fact is, arc flash events are rapidly expanding pressure. The temperature is up to 30,000 degrees Fahrenheit. It's 3 times hotter than the surface of the sun. The pressure wave expands at up to 200 miles an hour during these events. So if the equipment is close coupled, and the line side of the main is dangerous, unless you can show type testing, okay, and per IEEE C37.20.7, otherwise, it must be labeled PPE category dangerous. So one possible resolution, and this is a legitimate solution, is to physically segregate when you have a physical secondary main, the secondary main, okay, from the feeders. This does add to system cost. It adds to real estate, and of course, the main device, as is shown here, is still PPE category dangerous. You're still left with a large piece of secondary switchgear, which can never be accessed in an exposed, energized manner, which, by the way, makes it problematic even for absence of voltage verification in many cases. But if you can't do, I would argue this, if you can't do a secondary virtual main because the utility owns the transformer, physically segregating the secondary main breaker okay, from the feeder from the feeder circuits is the next best solution. Not as good as a secondary virtual main, takes up space, costs a lot of money, still at PPE category dangerous, but it is still better than close coupling those two pieces of equipment in terms of electrical safety and maintainability. So the problem, of course, with physical main are reliability issues. There's always a tremendous amount of arc flash incident energy. I shouldn't say always, but 99.9% of the time, your transformer is bigger than 125 kVA. You're going to have enough arc flash incident energy to cause injuries up to and leading to death, and permanently debilitating injuries up to and leading to death, as well as catastrophically damage the switchboard. This is a switchboard in a main tie main application where they thought they were safe, and it propagated to both sides, both the A and B sides of the switchboard, and destroyed everything. Okay? This was catastrophic. This was in a wastewater treatment plant, and caused sewers to back up throughout the town. So it's truly a catastrophic event. So in terms of physical main design summary, we readily acknowledge that if the utility owns the transformer, it's a secondary virtual main is not possible. In these situations, separating the secondary main from the feeders probably your best solution. Because secondary virtual mains though become so much more popular and make so much sense, we've seen many owners who previously have accepted secondary metering now move to a primary metering solution where they own the transformer, so they take the lower electrical rate that's offered by the utility that pays for the transformer. They own the transformer. Now they could control the primary and have both a safe and maintainable secondary distribution solution. A physical main device is usually more expensive nowadays. This is what's changed, I mentioned, in the economics. It requires additional space to install. If you go with a physical secondary main breaker, it requires additional, of course, maintenance over time. In most close coupled switchgear construction, whether you're medium or low voltage, it's no longer even useful as a lockout tagout point per OSHA IEEE or NFPA requirements. So not only is it useless in terms of arc flash mitigation inside the switchgear if you're close coupled, it's not even a good lockout tagout point. And then the last point to consider, the fifth point, is that physical secondary mains usually leave an unacceptably high amount of arc flash incident energy on the line side of the main device, which poses both safety and system stability, reliability challenges. So when we look in comparison at secondary virtual main and the safety and reliability advantages, I want you to look on both the left and the right. On the left, we have a physical main configuration, and on the right, a secondary virtual main. So here on the left, physical secondary main, we have PPE category dangerous inside the transformer, and PPE category dangerous inside the switchgear. So we have an inherently dangerous situation with respect to personnel safety, as well as danger to the equipment itself. The equipment can and usually is catastrophically damaged beyond the ability for field repair in these arc flash incidents. And as compared to a secondary virtual main, okay, and in this particular example, I want to say, in order to get the transformer down here, in addition to a secondary virtual main, we needed to add 87T, or transformer differential protection. And then the secondary virtual main frequently, usually, and again, you have to model this, okay, delivers less than 8 calories per centimeter squared at the IEEE 1584 working distance. So one of the two additional suggestions I would make if you are implementing a secondary virtual main, in terms of the primary switchgear, I would highly, since that's your lockout tagout point, I would highly recommend an isolation switch, an arc-rated isolation switch that's rated for C37.20.7. And what I mean by that is you can operate that isolation switch without any arc-rated PPE requirements. So it's a load break sealed isolation switch. Furthermore, my suggestion would be, and I could make this suggestion with or without a secondary virtual main, but it's particularly compelling for secondary virtual mains where we have a switch over a circuit breaker. As the switch is not the tripping device, you have an isolation switch and a circuit breaker, typically a vacuum circuit breaker, is to include an integrated ground switch. In this particular device, and Michael and I are not commercially connected to Schneider Electric. This was a Schneider Electric LBS kit solution that Mr. McClellan and L3 and Tech4 have frequently specified in switchgear we've provided via switchgear power systems. To add the isolation switch option is about $300. It's very, very little money. And now you have a 3-position switch that's closed, open, and then grounded with visible confirmation of blade disconnect, both for phase blades and grounding through separate front arc-rated viewing windows. It is a wonderful device. And I'll tell you, as much as I've preached this device to people, and they kind of listen, after we've delivered the device, this switch to customers, the maintenance people just fall in love with it. Because when you are used to getting to category 4 PPE, opening up the equipment, verifying absence of voltage with medium voltage equipment, with medium voltage test device, attaching a ground cable manually with your hand, getting out your hot stick and manually attaching the 3 grounding cables in order to establish an electrically safe working condition. So you've placed yourself at risk. It's hot, it's uncomfortable, and it takes a long time. In comparison to a completely safe operation, which, no exaggeration, takes less than 10 seconds. And I should add one other thing. In IEC land, in the International Electrotechnical Commission standards land in Europe, integrated grounding switches at medium voltage have been an IEC standard for more than a quarter century. So when Europeans come over to our country and they see us on new equipment, getting out manual grounding cables and hot sticks in PPE, they honestly think we're barbarians. Right? It's a very simple, safe device. Again, if I was in charge of standards, I'd make it a requirement standard 2 in design. I'm not. But in terms of secondary virtual main design, it absolutely makes sense. So in terms of design considerations for secondary virtual mains, I want to, both L3 and Tech4, we want to make clear that this is just one element among several that we believe you should consider in improving the safety and reliability of your electrical system. It helps a lot, but in and of itself, I would argue it's not sufficient by itself. It's a great addition, secondary virtual mains, to a holistic approach to safety and maintainability in electrical systems. The next thing we would point out is if you're going to implement a secondary virtual main, I would argue even for smaller transformers below 5 MVA in size, since you already have both CTs there and you have a protective relay, spend the few hundred extra dollars necessary to get a better protective relay, which incorporates transformer differential protection. So now we're not only reducing arc flash incident energy in the secondary switchgear, we're reducing arc flash incident energy and protecting the transformer itself. 87T, there is no better solution than differential protection. 87T for a transformer. I would consider adding arc flash mitigation protection either via zone selective interlocking, an arc flash protective relay, or if you're in a critical process environment, an active arc quencher system, which of course always guarantees in all application environments an available incident energy below 1.2 calories per centimeter squared. So active arc quenchers are the only solution prior to doing a power system study that we can tell you in 100% of cases always reduces incident energy below the level where arc-rated PPE is required. And of course, we do separate presentations on active arc quencher systems. And for primary switchgear design, so if you're going to use a secondary virtual main, and now you have a device on the primary side of the switchgear you could control. One of the things you can ask us breaker with a 12 millisecond opening time. So this is orders of magnitude faster than the next fastest 3-cycle or 50 millisecond breaker on the market. So if you take that 12-second opening time for the breaker and you add an arc flash protective relay to it, your total clearing time will be less than 16 milliseconds. You'll be you have better than less than one cycle total clearing time in terms of arc flash incident energy. And in a secondary virtual main construction, of course, that has a dramatic effect. In most of my models, at least an 87% reduction or more in secondary arc flash incident energy when you compare a 12 millisecond opening time primary breaker to one that takes 50 milliseconds to open. And by the way, 50 milliseconds is considered like a modern fast breaker. There's many vacuum breakers out there which are still 5-cycle or 83 millisecond opening time breakers. So this 12 millisecond breaker is really a game changer in terms of arc flash mitigation, especially when used with secondary virtual mains. And then on the secondary, whether you have a secondary virtual main or a physical virtual main, doesn't matter. We would always recommend when meeting the NEC requirements, high resistance grounding. According to IEEE, high resistance grounding doesn't reduce arc flash incident energy, but reduces the probability of an arc flash occurring by at least 95%, because at least 95% of arc flash events begin as single phase ground faults. And I wanted to show you a picture of that isolation and grounding switch I mentioned earlier. And these last two slides, Mr. McClellan asked me to add to the presentation, not really directly associated with secondary virtual mains, but we have almost always applied this equipment in conjunction with a secondary virtual main architecture. And this is the isolation switch on the line side of the primary breaker. This is that Schneider electric LBS kit switch. You can see the viewing windows here. So this is a cutaway view. There's two different viewing windows. One views the grounding switch or the grounding contacts, and one views the opening from the phase contacts. So again, this is a completely sealed arc safe switch. If your company policy allowed it from an arc flash point of view, this switch could be switch naked. There are no arc rated PPE requirements, and that's a bit tongue in cheek. Of course, you need safety glasses and other, long sleeve natural fiber clothing, but arc rated PPE absolutely not required. This is a picture of the circuit breaker I mentioned, and neither Michael nor I have a connection to this company, Tavrita, which manufactures these breakers, but we've used it successfully in many of the projects we've done with switchgear power systems in secondary main application. This is my favorite circuit breaker, and again, I don't have commercial connection with this company. We just like the solution it provides. This is the breaker we have provided, and it used to only be available fixed mount, and now it's available on draw configurations too. This shows the 15 kV breaker. They have 27 kV and 34.5 kV solutions available as well. But the key point here is up through 15 kV, either 5 kV or 15 kV applications, that key 12 millisecond opening time. And you combine that with 30,000 operations at full load, again, orders of magnitude more reliable mechanically than any other circuit breaker on the market. It's lightweight, maintenance-free, 5-year warranty. It is a game changer for medium voltage devices. And on top of all of that, it's very economical. It costs less than other medium voltage breakers currently on the market as well. So it's just a perfect solution with a secondary virtual main. So that's my presentation today on secondary virtual mains. I am now open for any questions, and I want to say again what a privilege it's been to be able to share a little bit of your time this Good Friday afternoon.
Mike, thank you very much. Look at your chat. We've got a whole conversation going on.
Okay. I haven't had that up because, of course, I've been.
Yes, I understand.
You know what it is, John? If I was female, I could look at the chat and do this because my wife can carry on a conversation with my daughter-in-law and type an email to my sons at the same time, but I cannot do that. All right, so let me open up the chat here. The males of our species can only do one thing at a time. Wow, we do have a lot of chats here. Okay. Oh, yes. Hey, Raj says he can hear me clearly. How does this virtual main compare? Okay, so one of the questions is, Mariano, how does this virtual main compare to just wrapping a differential from the line side in the line side of the primary main to the load side of the secondary main? Isn't there an argument this would cover a much wider range of arcing currents? Differential, so the answer is yes. Differential protection is a great idea, okay? And the wider you can make that, the more you can cover in that differential zone, go for it. But there's still a compelling argument, differential protection aside, to be made, that in a world where we understand now the physics of arc flash danger, that a physical secondary main, provided we can control the primary device, is useless. It doesn't serve any purpose. It takes up space. It's really expensive. It's useless as a lockout tagout device, okay? And it creates a piece of secondary switchgear unless you have your differential zone covering that, okay? Which is still problematic. So great question, but no, I agree with you completely. Which is why our argument is combining secondary virtual main with 87T. Oh, go for it. That's our preferred recommended design. Great question. And yeah, he noted here we already have the CTs. So if you already have relay class CTs, it's hey, I'll ask Michael McClellan or John Levine a question. How much does on a multi-lin relay? Okay, how much does it cost to upgrade from your simplest 5051 overcurrent protection relay to a relay that would also support 87T? Just off the top of your head, what's that cost?
We have a dedicated relay for transformer differential. So,
yeah, but the secondary main virtual relay can do overcurrent protection. You can have a basic overcurrent. There'd be a cost for that. To upgrade that to one that also has differential, has 5051, and now add in, the second set of CT inputs and 87T. How much more would that be roughly?
it depends on which relay I start with. I've got a relay that's 5051 for less than $1,000. I've got a 5050 relay that's $3,000. So,
yeah.
If I use my $3,000 relay and add differential, maybe you're talking, I don't know, $500, $1,000.
Yeah, $1,000. Yeah,
typically, I use a dedicated transformer differential relay versus a feeder relay.
And when you consider that versus the cost of the unit substation, the $30,000 or more you would invest in a secondary physical main, it's really minor cost in that respect. And there is one of the things Raj added. That's a very good point, Raj. He replied to Mariano where the 87T is for internal faults. So you're obviously comparing the current in one side of the zone to the other, and if they don't match after you account for the voltage difference, obviously that current's going somewhere else, and it is faster. It's differential protection is one of the approved methods of arc flash mitigation under 240.87 in the National Electric Code? That's very good. Great questions. Any other questions, gentlemen?
Mike, one thing I wanted to mention is your drawings when you're showing the virtual main earlier in the conversation was showing two relays, one for the medium voltage side and one for the low voltage side. That can be done with one relay.
Depending on the relay you have, that's absolutely true. That does not have to be two separate physical devices, depending on the relay that you have. Absolutely. And then let me see. Ramesh says it may be easier to install CTs on the transformer secondary than the virtual main switchboard. Otherwise, you are right about covering a wider range. Correct. Okay. You know, I would argue that although you're decreasing your differential zone, you're improving your arc flash mitigation where your overcurrent protection starts by moving the CTs closer. The closer you get it, in my opinion, to the transformer secondary bus, generally the better off that you are. Raj adds that secondary virtual main prevents higher fault currents on the feeder downstream. True. Ramesh says, if we are taking away the secondary main, what about all solutions out there about adjustable settings on the main, which allows lower settings during maintenance? Are these innovation solutions useless? All right. Great question. Okay, so first of all, just as we can implement a maintenance switch, which is what you're talking about here, which is lowering the instantaneous pickup point on a low voltage physical main, we can absolutely implement a maintenance switch if in a secondary virtual main protective relay as well. Okay, so that can be done. So the answer is yes, we can do that. But the second part of my question is, in Tech4's opinion, in my opinion, maintenance switches in general, low or medium voltage, bad idea. Now, I want to be clear. NEC 240.87 approves maintenance switches. So they list 7 different types now of arc flash mitigation solutions that are approved. And maintenance switches are one of them. We support all those arc flash mitigation solutions, but we will only implement maintenance switches at Tech4 if we get it in writing from a customer. And I'll tell you why I think it's a bad idea. One, there's no difference between a maintenance switch on a low voltage breaker, for example, and walking up with a screwdriver, okay, to the instantaneous pickup dial and dialing it counterclockwise to lower the instantaneous pickup point. Absolutely no difference. 2, we believe at Tech4 that protective device coordination exists in the National Electric Code for good reason. And when you engage a maintenance switch, either at medium voltage using a medium voltage relay or at low voltage with a low voltage trip unit, doesn't matter. When you engage a maintenance switch, you override protective device coordination. And you're overriding it when you need it most, which is when they're maintaining the equipment. The greatest probability of creating an event, any type of unexpected event, okay, is when the equipment's being interacted with. That's openly recognized in black and white by NFPA 70E. It's when we interact with the equipment that the risk is highest. So when the risk is highest, we engage a maintenance switch, which overrides protective device coordination when we need it most. So our argument would be, okay, that for any customer who's interested in a maintenance switch, talk to them about zone selective interlocking instead. ZSI is wonderful. It works. It's proven. It shouldn't really cost much more to implement than a maintenance switch. Okay, probably comparable. Might be slightly more expensive, but you always maintain protective device coordination. And there are environments, both in Category 3 and 4 data centers and in all hospitals, where you cannot implement a maintenance switch. In these environments, protective device coordination down to the lowest 120 volt receptacle must be maintained. Okay? So the bottom line is, yeah, we can do it with a second. We could implement a maintenance switch with secondary virtual main, but whether it's low voltage or whether it's a physical or a secondary virtual main, of all the arc flash mitigation techniques, maintenance switches are the one solution we believe is generally a bad idea. And not only that, I see people leave them on all the time. They turn the maintenance switch on, they've overridden protective device coordination, and it's left in a permanently on position. Lots of issues there. Great question. So John Levine noted the GE Multi-Lin T35, 845, T60 are all transformer differential protection that they offer. Donald Ray said personal protection is more important than coordination. Jumper the arc flash switch input always on, remove the chance that someone doesn't actuate the switch when they should, and coordinate using the faster trip time. That's an option, and again, I fully acknowledge that's allowed by the National Electric Codes, one of the approved methods of 240.87 mitigation. I find in most cases, people who implement maintenance switches, the implementation of a maintenance switch is to check the 240.87 box, because at 1200 amps and up now, you're required to do some form of arc flash mitigation. It's not a choice. Arc flash mitigation is now required in the plurality of installations, all 1200 amp and up, by the National Electric Code. That being the case, in our opinion, okay, maintenance switches are a demonstrably inferior solution in terms of system reliability compared to zone selective interlocking. I believe zone selective interlocking offers all of the advantages and none of the disadvantages that you would encounter with a maintenance switch. So great question. Mariano said, I have seen solutions where they take an auxiliary from the main switch out to a PLC alarm so the technicians don't leave them on. That helps, okay? So there are obvious solutions, okay, to leaving a maintenance switch on. The argument is you've increased your coordination. Remember, with respect to the conversation today, if your PPE category dangerous on the line side of your secondary main breaker, maintenance switch don't help you. And if you're close coupled, fine. Now you have you're lower on the secondary side. You've lowered your instantaneous trip point, but you're still PPE dangerous in the entire switchboard. Okay, but for many people, they feel that they checked the 240.87 box. Most AHJs I've seen accept that. Fine, you did something, but the switchboard itself, the device itself, is still PPE category dangerous. The real question is for you and your customers or the environment you're working on, do you really want to do something that improves system reliability and maintainability? Or do we just want to check the NEC 240.87 box, put in a maintenance switch, and move on? I will say this: maintenance switches are the least expensive, easiest form of arc flash mitigation to implement, no question. And there are ways to monitor it. Our argument would be, and you don't have to go to an arc quencher or an arc flash relay. Our argument would be zone selective interlocking is absolutely a better solution because it never overrides protective device coordination.
Mike, read Ramesh's last comment. That's a good question.
It says, I've seen most times the substation transformers are fed from a feeder breaker of the medium voltage switchgear. A feeder with a substation is fed from the feeder breaker of medium voltage. The breaker is not standalone. Is not a standalone to install an isolation grounding switch. The breaker is not okay, so you're talking, Ramesh, are you talking about existing equipment there and how you would implement an isolation grounding switch?
Hey, Mike, this is Ramesh.
Yeah.
Yeah, any place, even if it's a new installation.
Oh, if it's a new installation, we provide in the same cubicle. Okay, we provide a isolation switch on the line side of the circuit breaker. So you have an isolation switch on the line side of the vacuum breaker. Okay, so the and by the way, it's the isolation switch must be electrically interlocked, okay, with the vacuum breaker, particularly the vacuum breaker's draw out, because when the ground position, think about this, when the ground position of the isolation switch is engaged, you're grounded through the switch, the breaker must great. So I will tell you, switch over breaker configurations had become exponentially more popular because of NFPA 70E and the growth of popularity of secondary virtual mains, which was the topic of our conversation today, because that's now the lockout tagout point, right? And so literally the way this works from lockout tagout, Ramesh, okay, is you're going to open the vacuum breaker, okay, and I would suggest, as I did in one of my earlier slides, that you actually put the breaker control switch, okay, like in the secondary gear, so you're not standing in front of the vacuum breaker even when you open it. It makes people nervous, right? Safety considerations. You open the vacuum breaker. Okay. You walk over to the isolation and grounding switch. You open the switch and you have visible confirmation of blade disconnect through the arc rated window. Okay, per NFPA 70E Article 120.5. Okay, and then you move the switch to its third position, the grounded position. Okay, you lock it out in the grounded position, and again, visible confirmation of ground. Okay, through the arc rated window on the primary. We now go to the secondary gear, okay? And again, if you have a best practice design, you have a device like a Panduit Very Safe. Now, a Panduit Very Safe device per NFPA 70E replaces the need for a digital multimeter absence of voltage test because it's a positive voltage test device. It tests both phase to phase and phase to ground and tests the tester itself. So in literally less than a minute, I've locked out, tagged out, and put my substation in an electrically safe working condition. Go to work. You know, that's exactly how it works. So and you can do all of this, by the way, I would argue, for no additional cost than a traditional design substation with an air brake primary, fusible air brake primary, secondary physical main. For no greater cost, you can have dramatically improved safety and reliability, lower arc flash incident energy, all of the above. Great question.
So Mike, you're saying it's available in vacuum breakers right now? I know I have seen those in gas insulated switchgear. I'm not aware of those available in the vacuum solutions.
Right, so so let's look at the switch. So this switch in the one line is over this breaker, okay? So these are the two devices. Switch, you see the switch there, right? You see the slide?
Yeah, yeah.
Okay, that switch is only a matter of inches, okay, coming out the load side of that switch to the line side of this breaker. And this breaker can be in metal enclosed gear, fixed mount, or in metal clad gear, draw out. Okay, either one. Now, when you combine it, when you put it in metal clad gear, since the switch is not withdrawable, that's really classified from the IEEE point of view as hybrid switch gear at that point. But so even though the switch is load break rated, it's electrically interlocked, so the breaker here is always breaking the load, okay, in that respect. You can't, although the switch, that isolation switch here could be equipped with a shunt trip, Ramesh, it is not fault current break rated. It's load break rated, but not fault current rated. So you can't connect a relay up and under a 50-51 relay and under fault current conditions shunt trip the switch. That's not possible. It's not rated for that. The relay, the overcurrent protective relay must open the circuit breaker itself. But those two, you know, again, from a safety point of view, if you're going to rack out the breaker, okay, now you've completely isolated and grounded on the load side. So you're grounded, okay, to rack, and you're racking the breaker out under de-energized no load conditions as well that way. So rather than having the line side of the circuit breaker be hot for maintenance of the circuit breaker itself. So it's a switch over breaker configurations. But I'll tell you, you know, prior to 2006 or 7, I didn't see hardly any of these switch over breaker. You know, the last 4 jobs that we've been called on to design the road, the customer specified, you know, large international companies, isolation and grounding switch over breaker, because again, they want to do away with the danger and the discomfort and the time necessary to attach manual ground cables. They want integrated grounding devices, such as what is shown in this load interrupter switch construction. Integrated grounding is a wonderful idea. It should be wider. It should be adopted in a wider basis, in my opinion.
Mike, what's the ASC rating of that switch?
What's the what?
ASC rating, amps and rep.
Oh, great question. That is a limitation. Okay, so again, this not only the AIC rating, but the current rating. Like all switches at medium voltage, only 2 flavors, right? 1200 amps and 600 amps, and the AIC rating 25 kA. So that's a great question. If you have a medium voltage, where you have a medium voltage environment that's above 1200 amps or greater than 25 kA, yeah, that doesn't work for this. That's, if there's one, that is the greatest electrical limitation of using these switches. So, but I'll give you an example of that, John. We're doing a project now, Wapaka Foundry. They're the largest gray iron manufacturer in the United States, completely redoing their medium voltage infrastructure. And at the top level, we have 3,000 amp draw-out breakers, no isolation switches there. We have arc quenchers on each of those that protect the entire system. And then those feed, okay, 1,200 amp feeders, switch over breaker, and they had more than 25 kA. So we put in G&W current limiting protectors to lower the fault current to less than 25 kA. Because the transformers are huge, and they have 60 MVA and larger transformers, and it's on paralleling bus as well. So there are solutions when you have too much fault current, and the G&W current limiting protector is, in my opinion, again, the ideal solution to lower available fault current to a more reasonable level. Great question. Any other questions, gentlemen? Wow, it's a quiet group today, Mr. McClellan. Well, we are 9 minutes over. And again, I want to thank everyone. Please remember, if you're interested in a PDH certificate for the presentation today, that Mr. McClellan, Michael McClellan, has your name and your address. If you have any questions for myself or the L3 representatives, we specialize, again, L3 specializes in delivering the safest, most reliable electrical systems available, both low and medium voltage. And anything we can do to help you or your customers, we're always available to do so. So thank you again.
Good job.
Thanks, Mike.
Thank you.
Thanks, Mike.
Somebody just